perhaps a little bit towards the end, it's possible that we may try and have a little bit of a debate. However, there are some questions still hanging over, so I'd like to throw the first ones, Roger, to you because they're addressed to you. Okay?
Okay. Yeah.
So now, I have to tell you that I was having a discussion about the following question with Roger and Bill a few years ago, and Roger got so angry that he actually tore off his jumper and sat down and said, "I refuse to talk about this anymore." So the question is...
That's pretty bad. That's not usually my response.
The question is, many worlds seems to address the issues you have in your final model because it is deterministic and allows for observers to see different things. Why is it unpalatable to you?
Well, I have a theory about many worlds, is that it's something you ought to go through in your life at some stage. Whether it sticks with you is worse. And I can't remember how many weeks I did believe in this theory. Not many. It doesn't solve any problems. You still have all the superpositions, but you have to have a theory of what a conscious experience is. And presumably it threads its way through all these multiple worlds. And it's most unlikely that any of your friends will survive because their conscious experiences will have gone down other routes. It doesn't seem to me to solve any of the problems of quantum mechanics. But it's very popular in Oxford. The philosophers are all get keen on it.
Okay. There's a little another question which is perhaps also of interest to both you and Kip. So the question goes as follows. It seems that there are many theories applying quantum mechanics to explain space-time. Are there any space-time based theories of quantum mechanics? I think this is right up your street.
My street?
Yes.
Well, you can use space-time geometry ideas to describe, things like spin, for example. For example, this is the Majorana description of an arbitrary spin n state. Spin n over 2, let's say. Then you can represent that by n directions or n points on the sphere. And it's a very nice way of representing the general state. I don't know if that's part of the question here, but certainly geometry can be useful in understanding things which are regarded as essentially quantum mechanical. And I would regard this Majorana description of arbitrary spin states as one of them. Okay. Does that count as an answer?
It's possible that somebody was wanting you to spend the next 3 hours talking about twistors, but I think we'll try and avoid that.
Well, this is getting a little uncomfortably close to it, yes.
Yes, right, okay. Did you have any comment, Kip?
Well, I would just say that there was a lot of effort put in back in the 1940s, I guess. Well, beginning in the 30s, to understand special relativistic quantum mechanics, which is basically quantum field theory. And that really is, particularly the way Feynman formulates it, a space-time theory of quantum mechanics. It's you study all these histories in space-time, and you superpose them with the appropriate weighting functions, complex weighting functions, to get the probability of an outcome. So I would regard that as the kind of thing that's being asked about here, but it doesn't deal with gravity.
Right. Okay. This one was already alluded to by Kip, but I'm going to come back to it. I would note, by the way, you said that you felt that you were a bit of a loner in arguing that the information was lost in a black hole, but there are, in fact, two people in the front here who would agree completely with you, these being Bill Unruh and Bob Wald.
Yes, that provided a large amount of comfort.
Heavy duty, yes. And as a matter of fact, I would also agree. So, but the question is, for a lay person, What is the tangible and salient consequence of the resolution of the black hole information paradox, which I could rephrase as black hole information paradox, why should I care?
So let me just go to a physicist's point of view, but in language that may be helpful to the layperson, to the non-physicist. When we say information is lost, we're saying something very deep about the nature of quantum physics. And if information is lost, then the way in which 95%, 98% of the physicists think about quantum physics, do their calculations, is wrong. It's just simply wrong. And the only way to write that I know of is through Feynman's approach. And if there is something wrong with quantum physics at that level, and information is lost, that could have profound effects in the future for technology. I mean, it's a sudden paradigm shift. The way that we've been thinking about it in building all the technology that's built is simply wrong, and it's wrong in ways that may have future technological impact.
May I give my answer to this question?
Yeah.
I beg your pardon?
May I give my answer to this question?
Please.
My view is that if you have black holes, information is certainly lost because the singularity just swallows the information. And it's space-like on the whole. And if you get close to this thing, there's no way of avoiding it. The trouble is, it's not a paradox, because in my view, information is lost every time you make a measurement. See, people are talking about unitarity. They're talking about the Schrodinger equation, if you like. And information is not lost if you follow the Schrodinger equation. It's not lost if you have a theory which is so-called unitary, which is more or less a fancy way of saying the Schrodinger equation. Now, the thing is that is not information, it's quantum amplitudes. This tells you that to change that into probabilities, you have to adopt the Born rule, which tells you that your amplitudes are changed into probabilities. Now that never happens unless you violate unitarity. And the real world does violate unitarity because the state reduction, because of the measurement process. And in my view, the measurement process is a gravitational phenomenon. So that you can't expect unitarity to hold in the presence of a black hole, which is swallowing information. Yes, it does swallow information. It just gulps it down like anything. And the fact that it gulps it down like anything shouldn't worry you, because general relativity is dominating the situation. And you can't you can't expect unitarity in a situation which is as gravitational as that. Because gravity, when you bring gravity in, that's where the measurements take place. I mean, that's a view I have, which is probably not shared by everybody, but the view I have is that the actual process of measurement, which already violates unitarity, see, every time you make a measurement, it violates unitarity. But people don't seem to worry about that. You don't have to have a black hole, but you just have to make a measurement. And making a measurement involves violating the Schrodinger equation, as Schrodinger well knew in his description of this cat, which was to indicate how absurd the idea was that you could maintain a superposition of a dead cat and a live cat. So this is, I mean, it's clear people are going to get into trouble if they insist on preserving unitarity in the context of the black hole. You have a space-like singularity, and you can't expect the information to repeat itself outside the singularity. If it's going to repeat itself, it will violate quantum cloning. You have the non-cloning principle, which says you can't repeat the information elsewhere. But if you say information, you can't repeat the quantum state elsewhere. And the quantum state isn't information, it's quantum amplitudes it has. And to turn that into probabilities and things, or information or something, you've got to adopt the Born rule. And the Born rule doesn't follow the Schrodinger equation.
Okay.
I just don't understand how people address these mysteries. That's the trouble I have with it.
So I think one might remark then that it's not only Bob and Bill that are on your side, but Roger too.
We
Well,
seem to be a
absolutely.
hotbed of radicalism here.
Did you hear that, Roger?
I heard it was radical. But you see, I don't regard it as radicalism.
Oh,
I regard it as perfectly common sense.
okay. So there are two questions here that are closely related, and I understand from that one of these, and this is interesting, is being posed by somebody who's 6 years old in the audience. And the question is, what happens if a wormhole explodes while your arm is in it? So we have some very young members in the audience, it seems.
It's not pleasant.
You had it done to you, have you?
Your hand will wind up on the other side, and you wind up on this side, and the flesh in between has been caught in a singularity and destroyed along with space and time. And yeah, it's not good.
I have a theory that wormholes were partly my fault.
Sorry?
I have a theory, now that Kip's here, let me explain my theory, that wormholes are partly my fault.
Yes?
Because in my singularity theorem, I had to assume that you had a Cauchy surface. And Kip Thorne wrote an article for Scientific American, if I have it right, in which he was trying to describe this theorem. And he wanted to describe what was meant by saying you didn't have a Cauchy surface. And I said, something like, well, you don't join onto another universe. How do you put it like that? And that became wormholes, as far as I can make out. So I can't remember what Kip's article eventually said, but there was, in order to interpret the idea of not having a Cauchy surface, he had to say something like not joining up with another universe. And joining up with another universe was having a wormhole connecting you to that other universe. I can't say I like the idea of being historically involved in this concept, because it's not something I'm very keen on at all.
Okay. Now there's a question which I think is addressed to Marcus. Well, in fact, I don't think it is addressed to Marcus. If, when you do your experiments with big enough objects, quantum mechanics breaks down because of gravity, what will you see?
Well, a simple experiment you could envision is to perform a double-slit experiment. I already showed you this is being done with molecules, so you give the particle the possibility to go through both slits, and so if quantum theory holds, and if you prepare it in such a way that you cannot know even in principle which path the particle took, then you will see, when you repeat the experiment many times, interference fringes. So you will see a pattern at your screen that looks like a distribution. It looks like as if a wave would have passed through your experiment. So this is a signature that is indicative of quantum physics at work. Now, if for some reason, so let's assume I now do this experiment and I have a way simply to do that and increase the mass. So I do this experiment, I have a run with the molecule, and then the next day I do the same experiment and I increase the mass 10 times, I increase the mass 100 times, and so on and so on. And every time I check whether I do have an interference pattern. And I would expect that I will keep seeing an interference pattern when I increase the mass in my experiment. If at some point I stop seeing an interference pattern, then two things could have happened. The one is I simply have a mistake in my experiment. Somehow information or which path the particle took went out to the environment, or, so which means that quantum physics is still correct, but my experiment is not good enough, or quantum physics broke down. And it is now, of course, this is one of, since we were asked about challenges, so this is one of the challenges then for the experiments to double check whether your experiment went wrong or whether quantum physics went wrong.
So the answer is that you would see the interference pattern disappear.
Exactly.
Right.
But I need to make sure that it disappears. So I need to be sure why it disappears, because it can also disappear because of very trivial effects that I have a vacuum leak in my chamber. So that means suddenly I localize my particle. I don't see interference fringes, even though quantum physics would still be correct. So this is the not seeing a quantum signature is a difficult situation, because now you somehow need to really be sure in your experiment that it was because the theory fails and not because of the experiment was done badly.
Did you want to say anything, Roger?
Oh, well, I more or less agree with you.
I mean, I know you're not an experimentalist, but
No, I mean, you would, I mean, you could have one of these experiments, say like these Bose-Einstein condensate experiments. You put the system into the two places at once, and then you see, when you measure it, is it still in two places at once, or has it become one or the other? I mean, if the wave function, you have the system which is like a big wave function, the Bose-Einstein condensate. And so you can manipulate it like as though it was a big wave function. It involves many, many, many particles, many atoms, but it behaves as though all these things are pretty well in one state. And then you can do your two-slit experiment or whatever it is, put it into two places at once, and you will find the argument is that after a certain time scale, you see, the idea is that in the certain viewpoint that I hold to, well, you could say it's the Diauchy time, there is a time scale for that superposition. So we would expect, not exactly at that time, but over an average, within that time scale, it will become one or the other. So you have your two-peaked Bose-Einstein condensate, and you can sort of measure it as a way of doing that, and you can see, do you see a distribution in two places, or do you see the distribution has become one place? So I mean, it's I think fairly straightforward to see if this collapse has happened. Of course, it may be technically very difficult, so I wouldn't like to talk about the technical issues.
did you want to come back on that, Marcus?
See the big problem for such experiments, well, you could say, well, we've done it with the molecules, so just increase the mass by a factor of 100. So why are we discussing this even? And the problem is that the larger the object becomes, the more sensitive it is with respect to its environment. So the photons of the chamber walls that are warm, they will start to really affect my quantum system. So they can start to localize my quantum system. Tiny vibrations in the experiment will affect a massive particle much, much more than they do a small particle. So the more massive you make it, the more sensitive you become with respect to the environment. So this is why a massive quantum superposition is a very, very good sensor. So having that in the future might really be, could lead to incredible increase in sensitivity for dark matter searches or whatever. But the problem is also, if you don't control the environment, then you simply lose the quantum coherence, even though quantum physics is still correct. So this is the actual challenge. And control the environment so much that you can get to these large masses and then perform a controlled experiment.
Yeah, let me make a little comment about that. The drive to build LIGO and detect gravitational waves led to enormous advances in optomechanics, which are still having continuing to have an impact on all sorts of different branches of physics, experimental physics and technology. And I guess what you're saying, Marcus, is that the same thing will happen when in the drive to look for gravitational effects in quantum systems, that you have to develop new technology, new devices, which will then have a big impact on future technology. I mean, I think that's quite clear. I don't know if you both agree with that, but...
Let me just raise the issue, fairly obvious issue, that in the configuration that LIGO is now moving into, with injecting squeezed vacuum, rotating the squeeze angle, function of frequency, will be operating significantly below the so-called standard quantum limit. And we normally think of this as we are basically controlling the noise due to the photons that are making the measurement. But I think it really does also depend on the mirrors, 40-kilogram objects behaving quantum mechanically. And, but I don't know the status of, I've never thought about this in terms of let's make those mirrors classical. I mean, when I do the analysis of this configuration, I assume they're quantum mechanical and just do a straightforward quantum mechanical calculation. Will LIGO work in this configuration if these if the center of mass degree of freedom of the 40-kilogram mirrors is classical? I'm asking you. Or we can ask other people in the audience who know about.
Well, so I'm pretty sure Rana is here somewhere, so he will have to weigh in here. But the quick answer is yes, LIGO will continue to. So yes, LIGO will work. The question is, of course, when you do these sensitivity measurements beyond the standard quantum limit, you go below a noise level that is given by quantum mechanics, and that is given by quantum mechanics when you continuously measure your system. So you improve your sensitivity. The question is now, what happens if you add classical noise to the system? By how far can you then improve? And there have been guess you know better than there have been discussions, of course, about the thermal noise in in this optics, and this will limit the sensitivity.
Yeah, but that's the whole point. LIGO will have spent hundreds of millions of dollars to isolate these 40-kilogram particles just from precisely these kinds of effects. And so you're getting down into the regime where, at least the way I would do the analysis, the modified vacuum fluctuations beating against the laser light are manipulating the quantum state of the mirrors in such a way as to enable that, help that not get in the way of the measurement. Now, I think it is possible that if the mirrors were behaving classically, this would still work, and that the fundamental noise is really due to the light. But I'm not at all sure of that.
As far as I understand, there are two regimes. One regime where it is limited by the light, and the other regime where it's not.
Yeah. Well, in the regime where it will be operating next spring, you're in the regime where you've pushed the thermal noise, the classical noises, down to the point where they're not in the way of operating below the standard quantum limit. So, but anyway, this is getting too technical. But,
yes.
But let me just highlight the fact that we are dealing here with 40-kilogram quantum particles and issues of how they behave if something goes wrong with quantum mechanics that is central to astronomical observations that are being made in our era. And so this technology, the quantum issues, are part and parcel of major advances in astronomy that are going on.
Let me add a remark here. So Kip is talking about the importance of pushing quantum mechanics to larger and larger objects for LIGO and for astronomical observations. Marcus is talking about the same thing in discussing ways of testing in a very fundamental way quantum mechanics and the possible breakdown of it caused by gravity. And of course, people who are trying to build quantum computers are confronting exactly the same problem. And there's a name that physicists give to this. It's called decoherence. And it is one of the more important practical problems connected with all of these fundamental issues. And it has been driving and will continue to drive the development of quantum technology.
And this decoherence is central to what Roger's talking about.
Absolutely. Yeah, I think Roger agrees with that.
Oh, yeah, sure. No, these experiments, you're absolutely wrong. You have to make sure that the decoherence is kept to a minimum.
Yeah.
Then they'll mask the effect completely, otherwise, yes. But the trouble is, according to the point of view I would hold here, the decoherence itself is always using the collapse. You see, the wave function never should collapse at all, even with decoherence. But the only reason it does is because it gets so mixed up with all the degrees of freedom in the environment that you just give up. And you construct what's called a density matrix instead, which is really changing the rules. But it is decoherence. Your degrees of freedom have got lost in an uncontrollable way. They just spread out through the environment, and you just can't test how the quantum state is behaving at that point.
And now, as they say, for something completely different, the next question is, what is time?
John Wheeler gave us the answer. Time is defined so that motion looks simple. And the other answer, time, I don't know whether this was John's, and time is there to prevent everything from happening simultaneously. Okay, now somebody else can make a deeper answer.
Rod, you want to have a shot?
Well, it's in relativity, of course. You can't talk about time independently of space. So time is another thing which is defined universally. And I remember, I think in my book, it was one of my books anyway, I described two people crossing the street. I think they're just passing each other, walking past each other. And the question is, according to one of these people, the space fleet from the Andromeda galaxy has already set to destroy life on Earth. To the other person, the committee deciding on whether to send the space fleet or not hasn't been met. So when you have these very large distances or very, very quick times, and you're considering very fast motions, then the normal motion of time just doesn't work. There isn't, it's just the old Einstein simultaneity and so on. If you have moving bodies, then what is regarded as simultaneous, in other words, how you slice your space-time, is arbitrary and depends on who's doing the measurement, or whose clocks you're using, things like that. But usually it doesn't make any difference, because motions are so slow compared with the speed of light that you get away with having just one clock. Unless it's an extremely precise clock, then of course you can see the effects too.
I want to actually, is there a roving microphone anywhere? Great. One person who has very often addressed this topic in public lectures is actually Bill Unruh here. And I was wondering if, Bill, you could have a shot at this one too.
What is time?
What is time?
Well, it's as Roger has basically said, it's the same as space. So one could equally ask the question, what is space? One of the weird features of gravity is, and which is, I think, one of the things that is really one of the roadblocks to us developing a theory of quantum gravity, is that Einstein, one of the ways in which you can phrase Einstein's theory of general relativity is that gravity is the inequitable flow of time from place to place. Newton, in his Principia, one of his primary core statements, assumptions at the beginning is true and mathematical time flows equitably from place to place. And Einstein replaced that with true and equitable gravity is the inequitable flow of time from place to place. Once you accept that, then you can explain almost all of the gravity in this room, not gravity waves, but all the gravity in this room, just by saying that time flows differently from one place to the next, which sounds strange because what in the world does gravity and time have to do with each other? That sort of is one of the reasons why, I mean, quantum mechanics, the notion of time, the notion of unitarity, for example, is so inherent in at least our normal formulations of quantum mechanics that the fact that time doesn't behave the way in which quantum mechanics assumes it behaves, I think is one of the key barriers to finding a quantum theory of gravity that we're really going to have to get a hold of. And I mean, Kip with his time machines and so forth is just illustrating, you know, some of the features of this problem to quantum mechanics. Yeah.
It's also that
Thanks.
Marcus has already explained in experiments where the effect of gravity on the rate of a clock, like, can now be what was it, a millimeter? I can't remember what he said. If you raise it by 1 millimeter, then the rate at which that clock goes, as opposed to whether it's below or above, can be actually measured, the distance between the two rates.
Yeah,
Well,
this is what...
usually that's expressed as gravity causes clocks to move, to tick at different rates. But if you look at Einstein's general relativity, what it actually says is that time flowing differently from place to place is gravity. It's not that one is causing the other, it's that the two are identical to each other.
I'm not quite liking that formulation. So.
Okay. Kip, you had a question on that you wanted to address to
Yeah,
Bob.
so the definitive analysis of what I would call time machine self-destruction when you activate it was done by Bob Wald and colleagues. And I would just like to ask Bob what his attitude is toward his own result on this.
Yeah, well, the work you're talking about is done in the context of quantum field theory and curved space-time, where gravity is treated completely classically, but the matter fields or whatever else is present besides gravity is treated in a fully quantum way. I 100% agree with what you said, as that if we really want to know what's going on, we need a quantum theory of gravity.
Wow. Thank you. So the things that go wrong when you don't have fountains that I referred to, they are so bizarre and in some ways much less explosive that I'm pleased by your answer. I'm a little surprised, but maybe I shouldn't be.
No, I don't think you should be. And I mean, our result is also, it doesn't say in detail what goes wrong.
Yes.
It's a proof that something goes wrong with the stress energy tensor. It's infinite or undefined, but it doesn't give you some rate of blow up. But again,
I mean,
this is all done in the context of treating gravity completely classically and only treating the matter in a fully quantum way. So that's incomplete, and we'd like to know more.
Thank you very much. I think we're almost out of time here. And I believe that the final part of this day, I'm programmed to give a summary and also what is called a call to action.
So we'll leave and
Yeah, you might want to. Thank you so much.
You want me to get rid of that?
Yeah, sure. Yeah, go ahead. Roger, by all means, stay online.
I think I'm going to go to bed. It's 1 o'clock in the morning.
It's only another 10 minutes. And since you're a board member, you might be interested in what's
All
going
right,
to be
well,
said.
I'll give you another 10 minutes.
Okay. I can't believe you're still up.
It's not all that late for me. It's only 1 o'clock. It's big after 1.
Should I be using this microphone or the main microphone? This one's fine? Okay. Okay, so I don't think there's any point in me trying to give a long summary of what you've heard. It would just take up time. So let me just summarize by saying that in the morning we heard all about the universe, and in the afternoon we got down to brass tacks, as they say in Britain, and we started to look at things like what kind of experiments on Earth might be done and what one might see. And as you've seen, Roger's commented on that. And then we also got I would say, a profound analysis of what might come out of a theory of quantum gravity, at least in one sphere, that is from Kip Thorne. So now I'd like to, I mean, that's the summary, okay? Pretty short. But I was asked also to simply address the question of what next. And I think that I'd like to say a little bit about what got me into this and what got the board. I already mentioned that briefly, and people on amongst the founders have discussed that, although Roger never had a chance to. I myself started university doing philosophy and literature, but on my 18th birthday, my mother gave me a copy of what is called the Telephone Book. For those of you who don't know, the Telephone Book is this monstrously large book written by Kip Thorne along with John Wheeler and Charlie Missner on gravitation, and it set the tone for research, certainly in the West, or even now. And then when I went to university, I got I missed out part of the story. Like Frank, I was a bad actor at school. I think he was probably worse than me, because didn't you tell me they threw you out? Twice. Okay. And I remember being called to the office of the principal, and to my astonishment, he wasn't asking me why I was skipping school all the time. He wanted to know why I refused to believe in quantum mechanics. And he pointed me toward some books, the Feynman Lectures on Physics, which, and I have to say that these two books are what induced me to go back from philosophy and literature to physics. Well, later on, I got involved with doing experiments in low-temperature physics and in condensed matter theory, and this was actually largely under the influence of somebody who couldn't be here either, and that's Tony Leggett. He's not traveling right now because of COVID. And all the while I was doing this, I knew from having studied these books when I was 18 that the real problem lay elsewhere. And it's the problem we're discussing today, how to unify the two great theories of 20th century physics. But it wasn't until I actually got into a long discussion with Joe Polchinski, whom Kip mentioned, that I actually decided to work in the field. And that was quite a while ago. One thing that's become very, very clear to me, and as you've heard to people working in this, is that even though people have been working on this problem now for a very, very long time, all of a sudden, it looks as though we might actually be able to finally get to grips with it, to finally confront gravity with quantum mechanics. And so that day of reckoning, if you like, may not be so far away. Marcus was asked in some question, you know, how long before the jaws closed, and I thought he was rather evasive, actually, in his answer. But if you look at the timeline on his graph, it actually looks like it'll happen in less than 5 years. He's not saying anything, but pictures speak louder than words, Marcus. So, and as we've just discussed, actually, the advances that are now being made in quantum technology are very much connected to this really fundamental search. So what do we do now? Well, actually, the discussions between myself and the other founders, and we had a very, very brief picture of them at lunchtime today, revolve also around practical questions. And I have at one point, I described to them, I think it was actually Terry Hui who really ran with this one, because he's been very enthused about the idea of comparing this meeting with the Solvay meetings. So let me recall a little bit of history. Back in the 1920s, it was pretty clear to some physicists that something really big was going to happen in physics. They didn't know what, but it was clear. And the very first theoretical physics institute in the world was founded by Niels Bohr in Denmark at that time. The money came from Carlsberg, whom you all know as beer manufacturers. But they basically put up the money to found this institute. Bohr was very clever. He surrounded himself with what we would now call postdocs. And these people are household names, at least in physics. Heisenberg, Pauli, Dirac, Landau, Platschek, Kramers. And with the sole exception of Schrödinger, these were the creators of quantum mechanics. And so a lot of it was done in this one place. And you notice it wasn't big, it wasn't populated by hundreds of people, it was small, but they focused on the right problem at the right time. And at the same time, there were these Solvay conferences that Terry is so enthused about, which essentially also happened at the right time and provided the venue for these people to discuss what they'd found with everybody else. And that's actually the main reason why quantum mechanics, when it was discovered, spread so quickly via meetings like the Solvay meetings and with their genesis in a small institute. So this has actually guided some of our thinking. And so Paul asked me to make a call to action. And he asked the question, why on earth would this not happen in Vancouver? I think he was referring to the fact that, you know, there's this tendency in Canada to assume that if anything important is going to happen, it'll happen somewhere else. And I remember telling a story to him. This happened in Vancouver back in 2002. I just actually moved here. And there was a big conference downtown in the Vancouver Convention Center. It was organized by all sorts of people. And their thought was that they would have a nanotechnology center in Vancouver. And there was all sorts of discussion of this. And it was, I think in the end became clear that there wasn't enough will from the politicians. But I remember a venture capitalist from Austin, Texas, getting up and making a speech. And he said, well, you know, I've had a lot of experience setting things up in various cities, Sydney, Austin, Edmonton, Shanghai, etc. And he said, and you know, I learned something from that. He said, I learned that Canada is like New Zealand. And my ears perked up when I heard that, because that's where I spent my childhood. And he said, they both think of themselves as much more civilized neighbors to much larger, uncultured countries. He said, but there's a difference. He says, when the Kiwis go up against the Aussies, they expect to win. And I can tell you, there was a lot of passive aggression in that room right after he said that. And he said, and the other thing, he says, the Americans always play as a team. And then he didn't say anything more. Well, I think that Paul's reaction to that was pretty much like mine, which was, the hell with that. There's absolutely no reason why we can't reproduce what they did in Copenhagen, which at that time was a complete intellectual backwater. So, my call to action is, let's get going. Thank you.